Okay, welcome to lecture 21. So today we're going to be going through an example of the spring mass system which we learned in the last class. So we're going to be going through an example today both by hand, and then I'll also show you how to do it using Octave, or the same method for MATLAB as well. So the example we're going to be looking at today is what we were calling case 3. So the case where we have damping beta is non-zero. So here you can say beta is 2, you can see the beta over mass is equal to 2. And also the right hand side of the equation is non-zero. So we have a non-homogeneous equation. Here you can see this is 4 times cosine of 2t. So this, I'm going to say here that this is some second order linear non-homogeneous ODE with constant coefficients that represents some spring mass system. Okay, so with this initial value problem, in fact, we have some initial conditions. So where you can see from the initial conditions that at time t equals 0, the mass is in the equilibrium position because x is equal to 0 at time 0, and also it's not even moving at time 0. So at time 0. The velocity is equal to 0. So the mass is just sitting in its equilibrium position, not moving, and then somebody exerts a force on it. Okay, and so in fact this is some periodic force as well. So from this equation we can identify these constants. Lambda is equal to 1, omega squared is equal to 2. So well, omega squared is just the number in front of the x here, so 2. So omega squared equals 2. Lambda, well, 2 times lambda in fact is this number in front of the velocity here, the first derivative of x. So 2 times lambda is 2, so lambda is equal to 1. Okay, and remember this is a non-homogeneous equation, so we need to solve this in 2 parts. We firstly need to find the complementary solution, which is where we solve the associated homogeneous problem, and then we can let's use the method of undetermined coefficients to find a particular solution to this non-homogeneous equation. So firstly, let's solve the associated homogeneous problem. So taking this equation, making it homogeneous, the right hand side equals 0. Okay, so the auxiliary equation for this homogeneous problem is going to simply be m squared plus 2 times m plus 2 equals 0. Okay, and now if you solve this equation using the quadratic formula, you'll find that we have 2 complex conjugate roots. Okay, so we get m1 equals negative 1 plus I, m2 equals negative 1 minus I. Okay, so we can identify the real part of this equation as being negative 1 and the imaginary part as being positive 1. And so the complementary solution we can write down straight away because we're really good at doing this now. We can write that down as being xc, complementary solution, is equal to the exponential of negative t, so the t times the real part of this root, so negative 1, times c1 cosine of t, so here our imaginary part was just 1, so we just get 1 times t, plus c2 times the sine of t. So if you practice solving second order homogeneous linear equations with constant coefficients, finding solving these problems, these homogeneous problems, they should become second nature to you. Okay, I can't really amplify that point enough, that I really would like you to be able to solve these second order homogeneous ODEs, linear ODEs with constant coefficients. I'd really like them to become second nature, so please practice as much as you are able. Okay, so the complementary solution we can find rather quickly. To find the particular solution to the non-homogeneous ODE, we're going to use the method of undetermined coefficients. Okay, so here's our initial value problem. Here's our complementary solution. We can write down a test case for a particular solution, noting that, firstly, we should note our non-homogeneous term is the cosine of 2t. Our complementary solution contains the term cosine of t. So 2t is not the same as t, so the solution to our complementary, to our particular solution is not going to be bothered by this complementary solution because cosine of 2t is not the same as cosine of t. So we can write down then a particular solution, some constant c3 times the cosine of 2t plus some constant c4 times the sine of 2t. Because remember, when we're using the method of undetermined coefficients, if we have a trigonometric term, cosine or sine, on the right hand side, when we check out our particular solution, we have to include both cosine and sine. Even if there's only cosine up here, we need to include cosine and sine here. Okay, well, according to the ODE, we need to calculate two derivatives of this particular solution here. So if we take the first derivative, we're going to get negative 2 times c3 sine 2t plus positive 2 from the sine here times c4 cosine of 2t. And then similarly, if we take another derivative, we're going to get negative 4 times c3 cosine of 2t plus 4, this should be negative, I think. This should be negative 4 times c4 of sine of 2t. Okay. So I just quickly changed that to negative because I missed that in my slides. Let's continue. So using these three relations, one for x, the particular solution x, one for its derivative, and one for its second derivative, in this original non-homogeneous ODE, we get this lovely expression here. Okay, so let's take this term by term. The first part here is the second derivative of the particular solution. So in the original ODE we had x double prime. Here's the second derivative of the particular solution, and we've written it here in the expression here. Here we have the next term is going to be 2 times x prime of the particular solution. We wrote down here, so we write that in this term here, and then we had 2 times x itself, so we get 2 times xp down here, and then of course the right hand side is just the non-homogeneous term, 4 times cosine of 2t. We can solve this by matching terms. Okay, so if we look at the sine terms, well, let's work from left to right here. So this is a cosine terms. Here we have negative 4 times c4 lots of sine 2t, so negative 4 c4. Here we have plus 2 times negative 2, so again negative 4 times c3 times the sine of 2t, so negative 4 times c3 lots of sine 2t. And the third term here we have 2 times c4 lots of sine 2t, so plus 2 times c4 lots of sine 2t, and that's equal to 0 because there's no sine of 2t on the right hand side. And now if we work through the cosine terms, well, again from left to right, we have negative 4 times c3 lots of cosine, so negative 4 times c3 plus 2 times c4 cosine of 2t, so 4 c4 cosine 2t plus 2 times c3 cosine 2t, so 2 times c3 cosine 2t. And on the right hand side we have 4 lots of cosine 2t, so the right hand side equals 4. So now you see we have two equations for our two unknowns c3 and c4, so we know that we can solve this system, right? We can simplify first by okay, here we've got negative 4c4 plus 2, so we're going to get negative 4c3 minus 2c4, and similarly we get 4c4 minus 2c3 here equals 4. So we can simplify that equation, and you can solve this equation however you like, but you should find, if you try this, that c3 is equal to minus 2/5 and c4 is equal to 4/5. Okay, so this is our particular solution here. Notice that we did need both the cosine and the sine part to solve this non-homogeneous equation. So finally, our solution to this example is xc plus xp, so the complementary plus the particular. So in green here, this is the complementary solution we found to the associated homogeneous problem. And then in purple here, this is the particular solution that we just found using the method of undetermined coefficients. Okay, so then we're almost done now. The only thing we have left to do is use our initial conditions to solve the initial value problem itself, right? So, well, we know that when t equals 0, we know that x is equal to 0 by the first initial condition, okay? So let's see what happens when we substitute t equals 0. In our solution, we get e to the 0 is just 1, times c1 times cosine of 0 is 1, so we get c1. Here sine of 0 is 0, so we get this whole first term here, this complementary solution, just reduces down to c1. And the next part here, again, the sine term becomes 0, so we just get negative 2/5. Okay, so we end up with 0 equals c1 minus 2/5. So there, clearly then, c1 is equal to 2/5. To calculate the second, well, to use the second initial condition, we have to take the derivative of our solution here, our general solution to the non-homogeneous ODE. Okay, so, well, it's a little bit tricky because we've got exponential times a cosine and exponential times a sine, so we're going to have to use the product rule here. But when we take that derivative, this is the expression we get. Okay, and again, I'll leave it to you to again try this derivative because it is something that is from first year calculus. But again, if you get stuck, you're always welcome to get in touch with me. Alright, so let's, now that we have an expression for the derivative of x, let's use the second initial condition. When t equals 0, this velocity, or this first derivative of x, is equal to 0. Okay, well, if we do that, then, well, again, this exponential term is going to negative 1 here. Cosine is going to 1, sine is going to 0, so we just get negative c1 here, plus 1, well, this is 0, times c2 of 1 times 1, so we get plus c2, so negative c1 plus c2 plus 0 plus 8/5. Okay, well, we already know that c1 is 2/5, so we can solve that equation and find that c2 is equal to negative 6/5. Okay, we can use then c1 and c2 in the general solution to the ODE to find the solution to the initial value problem, like so. Okay, so this first part, this complementary solution here, was the solution to the associated homogeneous problem. As t goes to infinity, this exponential goes to 0, okay? Cosine and sine but stay between negative 1 and 1. So this first part here, which we got, which is the complementary part of the solution, this is also what we call the transient part, because it approaches 0 as t gets large. And the second part, well, this is always between negative 1 and 1. It never asymptotes to 0, so this is called the steady state solution, or the steady state part of the solution. We can also show that the amplitude and the phase angle are given as square root of 8/5, and the phase angle phi was 2.8198. If we were asked those questions as well, but in fact the solution we've got here is fine to solve the initial value problem, unless we were specifically asked to find the amplitude and the phase angle. Okay, so we've solved a problem by hand here, or yeah, on the slides here. Now let's transition over to Octave to solve a problem using the Octave. I'll use Octave Online, but in fact it'll be applicable to MATLAB as well. Okay, so we're going to solve actually the same example of the second order differential equation, or the second order initial value problem, in fact, using Octave. Okay, so actually I just checked, and the commands for MATLAB are ever so slightly different than Octave. So if you are using MATLAB, then perhaps what you might like to do is go to the class stream site. I've got a lot of classes here. Go to the class stream site and download the MATLAB or Octave for Differential Equations 1 workbook. Okay, and in there you'll find some examples of solving these ODEs using MATLAB. Okay, so we've got direction fields in here and higher order ODEs. Where is it? Right, so in this Unit 1 section here, this will tell you how to solve ODEs using MATLAB. Okay, but just so that we've got some flexibility here, I'm going to show you how to use Octave Online to solve these ODEs. Okay, so create a new file here. So maybe I'll call it solve my ODE. Okay, and I have to click on that. Solve my ODE. I'll get rid of that junk text. Okay, so the first thing I'm going to do is just clear everything. So clear all, close all, and CLC, which is clear the command window, just to make sure that everything, there's nothing displayed on my command window. This keeps it clean. Sorry, X of t. So the first thing, then I'll define this symbolic variable x, and x is a function of t. Okay, so x is a function of t. Let's define my differential equation, dE. Okay, well, my differential equation was the second derivative of x plus 2 times the first derivative plus 2 times the variable x equals 4 times cosine of 2t. Okay, so let's enter our differential equation, and so to get the second derivative, I'm going to write diff. I want to differentiate x with respect to t 2 times. Okay, so this term represents the second derivative of x with respect to t. Okay, I'm going to add 2 times the first derivative of x with respect to t plus 2 times x itself is equal, two equal signs here for Octave, 4 times cosine of 2 times t. Okay, so this is the differential equation. I'm going to add this little semicolon here so it doesn't print that every time. The solution to this differential equation we can solve using this dsolve command. Okay, so dsolve, I'm solving the differential equation with some initial conditions. Okay, my initial conditions were when t equals 0, x is 0, and when t equals 0, the velocity, or the x prime, is 0 as well. So I'm solving my differential equation with the initial conditions. X at 0 is exactly equal to 0, and the derivative of x at 0 is equal to 0 as well. Okay. So let's save and run that and see if it solves and gives us the same solution. Okay, great. So here we get e to the minus t, exponential of minus t, times negative 6 over 5 sine t plus 2/5 cosine t. So let's just check. It's the same. E to the minus t, negative 6 over 5 sine t plus 2/5 cosine t. So good. And then we're going to have minus 2/5 cosine of 2t plus 4/5 sine of 2t, which is exactly what we have down here. So we're solving this exactly perfectly using Octave. Okay. But also we might like to plot this this command, and this is something that's a little bit harder in Octave. So this is a symbolic solution here. So what I have to do is take the right-hand side of that solution. Okay, what I'm going to do is I'm just going to call, well, maybe I can call this sol plot, so solution to plot. I'm just going to type function underscore handle the right-hand side of sol. Okay, and if I save and run that now, you'll see that this thing solve plot is now the right hand side of that solution to the ODE. Okay, so here's the ODE in symbolic form, and here's the right hand side of that solution. So now I can plot, well, let's use EasyPlot. I'll EasyPlot the sol plot between, well, t equals 0 is our starting condition. Let's go to 5. And so this should plot the, plot should have a capital P. This should plot the solution between t equals 0 and 5. Okay, great. So here is the solution between t equals 0 and t equals 5. You can see that you have some small oscillation and then some larger oscillation. Let's also see what happens if we plot this over a slightly larger range. So let's say t equals 0 to t equals 50, just to see what the longer term behavior of the ODE is. Okay, I might have to add 15 seconds. There we go. Okay, great. So you see that initially you get this small transient jump here, which doesn't quite reach 1, but then very quickly you move towards some kind of transient solution where it's not quite equal to, it's equaling some steady state solution. So this transient term in the solution, this first term here, this transient part, this dissipates very quickly, and really that's because we've got this exponential here, exponential of minus t. As t gets larger, that really goes to 0 quite quickly. So that's why we reach some steady state solution very fast, in fact. Okay, so that was a really quick example of how to use Octave Online to plot, solve and plot ODEs. In fact, to solve initial value problems, because we had 2 initial conditions here. It's similar in MATLAB actually, not exactly the same. So if you're using MATLAB, please check out the workbook. And again, feel free to get in touch if you have any questions or need any help with that. Okay, thank you very much.